Ides of March. Do you guys know that? Do you have the opportunity to read Julius Caesar? Have you guys done that or no? Is that not on your list of things? There is a movie. Yep. So Shakespeare's Julius Caesar was one of the big tragedies, right? I had the opportunity to read it when I was in 7th grade, and you know, when you read plays, the teachers always kind of assign parts for a day or whatever, and I thought it was really lame at the time, but I was the soothsayer, which is like the, like person who tells, and that's the one that basically tells the main character that he's going to be killed. So there you go. Yeah, so I knew what was going on. I had some sort of premonition. It's not something that's in my personality normally, but yeah. So anyway, Ides of March, 15th of March. They tell you to beware of it. The reason that I bring this all up is because I want you to be culturally literate. Okay, people will say that beware the Ides of March means watch out, right? The reason is because the soothsayer was telling Julius Caesar that he was going to be killed on the 15th of March. And indeed, he was. And the story goes on from there. Yeah, lots of death and destruction as per usual with Shakespeare's tragedies. There you go. All right, today we are going to jump in. We're going to talk about sound waves and then spend a little time at the end talking about resonance, and that will get us through to spring break. Woo! And then after break, we'll do some labs and stuff, and we'll, go from there. I want to remember here, we did standing waves yesterday, right? And we talked about stuff, and then did we make it through both of these? Were we okay with this by the time the bell rang? Everybody was happy? Is that right? Yeah? Okay, cool. I just wanted to make sure that we were there. I didn't put up going through homework today because I didn't want to bog down things, and I also was making a educated guess that maybe not everybody got their homework done for today. Maybe that's true. Maybe it's not. Maybe you did your homework, and if you did, you're awesome, and I appreciate that. If you didn't, I would strongly encourage you to spend, a few minutes over break, just getting yourself caught up, because we're going to have another quiz coming up pretty quick. All right. So we're going to talk about sound waves today. So I'm going to have you on a new paper or on a new section of paper, write down sound waves. And then I'm going to give you just a couple minutes to write down everything that you know about sound waves. What kinds of things do you know about them? All right. Friends, what do you know about sound waves? Tell me something. What's that? Longitudinal. They are longitudinal. What does that mean? What does it mean to be a longitudinal wave? So Megan's going zoop, 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 zoop. Isaac's going zoop, 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 zoop. Yes. What's the purpose? What is a longitudinal wave? What's they?
The longitudinal wave is when the medium moves parallel to the direction of the wave.
Yeah. So the medium moves parallel to the wave motion. So the reason that I wanted you to articulate that really clearly is that sometimes we get in our head and we start dancing, right? And so if you're asked a question on a test, what does it look like? What does it mean? And you start dancing. That's really cool, and I like the enthusiasm, but that might not translate to a correct answer on a test. Do you know what I'm saying? Or a quiz. So that's why I want to make sure that you really know that it's the medium that's moving parallel or perpendicular, in this case parallel, to the wave motion. Okay, so sometimes we draw that, sometimes we dance that, but I want to show you what that really means when we're coming into a sound wave. I'm going to do that in a second. I just realized that I totally cut us off from our brainstorming time. What else do you have? Because you had something else besides just that it was a longitudinal wave. What else did you say? What other things do you know about sound waves? There's got to be something. Sam, you had more than one. You had two things written on your list. So what's the other one?
Different pitches travel at the same speed.
Oh, I love that. I'm so glad that you said that. It's very true. Yeah. Different pitches. And there's actually a lot of physics in that statement that you just said. So different pitches. I'm going to write down what you said, and then we'll kind of dissect it a little bit. Travel at the same speed. Is that what you said?
Yep.
Okay. I didn't want to put words in your mouth. So we've said this a little bit, but now since we're officially talking about sound waves today, I want to make sure that we know what pitch means. How many of you have played an instrument or sung in something besides a kindergarten choir? Had some sort of musical experience? So you may have an idea of what pitch means. If I say something like high pitch, what would that sound like to you? Could you make a high pitch sound? Go.
That right there, that little tiny one.
The little tiny one. Why do you say little tiny one?
It's like super squeaky.
It's like squeaky, right? Like right? Like that's super high pitch. Now, as compared to that, now that you all have as your high pitch like image or your thought in your head, what does low pitch sound like? Make the noise. Come on.
Do it.
Come on, Isaac. Come on, Megan. Come on. Ben, what does it sound like? It's lower, right? Low. Yeah, so you got high pitch and you got low pitch, right? How does pitch? That's beautiful, friend. How does pitch relate to frequency? Do you know?
Huh?
How does pitch relate to frequency?
You have a high pitch, you have a high frequency. You have a low pitch. Yeah, which one's that?
Yeah. So a high pitch. So pitch literally is something that's interpreted by your brain. Okay. So have you ever heard of somebody who has perfect pitch? You ever heard that? I had a student once who had perfect pitch. Like she was an insanely amazing musician. And she had so you could just name a note and she could sing it. Like that's like what? It was amazing. But that is because her brain interpreted things just the right way, according to the right way that we say things, right? Not everybody has perfect pitch. We have a really good friend who really likes to sing karaoke and cannot carry a note, he doesn't hear it well, you know what I'm saying? And so it's he loves doing it, but it's always that sounds pretty bad. Oh my gosh, right? So his pitch is not perfect, but that doesn't mean that they're hearing that the notes don't work. Do you know what I'm saying? It just means that their brain interprets it differently. So pitch is really it's our internal process of the sound waves that we hear and their frequency. So frequency is the quantitative value. That's the thing you can measure. Pitch is the internal interpretation of that. But the thing to know is that the higher the pitch, the higher the frequency. Okay. What else was on your list? Ben, did you guys have anything else back on your list over there?
I said speed relies on the air temperature.
Okay, so that comes to, I appreciate you saying that because that comes to the second piece of this. So different pitches or different frequencies travel at the same speed, but only when they're traveling through the same what? Temperature, the same medium, right? Same speed in the same medium. So that means exactly the same. So if we're talking about air, we know that temperature matters. And so if you have really, really cold air versus really, really warm air, you have different speeds. Question. Can sound travel through things that are not just gases? Can they travel through solids or liquids? Can sound travel through a solid or a liquid?
It can.
Do you have, what's that? The question was, can sound waves travel through a solid or travel through a liquid?
Yes.
You have evidence of this, right? What evidence do you have that this is true?
So if you're because when I was little, I used to play the game can you hear what I'm saying underwater?
Yeah.
You can still hear the sound in person. You might not hear what you're saying, but you can still hear the sounds.
Absolutely. That's exactly right. It's like when you're playing at the pool, right? Absolutely, you can make a sound and that's going to vibrate the water molecules just like it vibrates the air molecules. It might sound garbly because you're also getting all that other sound, right? And it might not make a lot of sense because the articulation is different, but absolutely. So that's another thing we could write down. Here's another one. I hope I'm not stealing somebody else's thunder from something on their list, but I'm going to write it down here. And that is another thing about sound waves. They can travel.
You can also think about Harry Potter when he puts the gold egg in the water and she starts singing.
There you
I
go.
watched it last night.
Yeah.
Through
It was on TV.
solid,
Yeah.
liquid, and gas. Now, we are convinced that sounds can travel through gases because you can hear me talking. We're convinced that we can hear things through liquid because Ben had that experience when maybe it was last week, I don't know, but whenever. Can sound waves travel through a solid?
Yeah.
Evidence for that.
Tin can and a string.
Tin can and a string, right? Have you ever, go ahead. Were you going to say something?
No, I'm just.
Have you ever been in, I'm just thinking like in a house, you shut the door because you want some privacy or whatever, and then, somebody's like, oh my gosh, your music's too loud, because they can hear it. And it's because it's traveling through the walls, right? It's traveling through the door. It's traveling through those solid things. Absolutely, it can travel through solids or liquids or gases. Does it have to have a medium to travel?
So I was gonna say, is sound wave a weave of mechanical waves? Is it like
Wait, say that again?
It's like, is it under a mechanical wave?
Yes, sound waves are mechanical waves.
Mechanical waves need a medium.
They do need a medium. So that would be another thing for us to write down, wouldn't it? That sound waves must have a medium through which to travel.
Electromagnetic.
Right, and we'll get there. Yeah, but after break. Yep, through which to travel. Okay. I'm going to come right over here and grab my handy dandy tuning fork so that we can talk about a couple of things and make this make a little more sense. So I don't know if you've ever seen a tuning fork before. A tuning fork is just a piece of metal that has been manufactured or shaped to look kind of like a two-prong fork, I guess, okay? And basically what it is, it does the same thing that a pendulum does. Do you remember when we were doing the pendulum when it swung? What was the thing that the pendulum's frequency or period depended on? Do you remember?
The length of the string.
The length, right? And as long as you have a certain length, it was always going to do the same thing. Same deal with these. So these are manufactured such that they're going to vibrate at the same frequency. Remember, frequency and period are all the same thing. So, I mean, they're not the same, but they're, inverses of one another. So you've got all of that there, right? So I'm going to strike this tuning fork, and you can hear it. Oh, it's so nice, right? Okay, so then Emma's going to look at this little thing that's stamped right on here. What does that say right here? It says C, and then it says C256.
Is it keep going?
Yeah, for a long time. Yeah, because it just vibrates back and forth and back and forth and back and forth forever. Just like your pendulum will vibrate back and forth and back and forth and back and forth forever. You with me there? So it'll just keep going for a long time. And as it's doing that, it's going to stay the same note the whole time. Do you notice that? It might get a little bit quieter. Quieter means that the amplitude is going down, but it's the same note the whole time. The same note, and what note is it? C. It's middle C. Okay? The 256 means that it's vibrating back and forth 256 times every second. 256 times back and forth every single one more time. That's really, really crazy, right? So the reason that you hear it is because the little tines of the fork, and I'll come around so you can see it again in just a second, but they move back and forth like this, right? And they push the air back and forth like this 256 times every second. That pushes the air, that hits her eardrum. Can you still hear it?
Yeah, it hurts. I don't like it.
I'm sorry. Was that hurting you? You should have told me to stop it. I'm sorry. Didn't mean to hurt your ears. Just wait. It'll get worse. I'm sorry. It'll be okay for now. I won't play it anymore. So 256 times every second, that air is being pushed. And then as soon as that air disturbance gets to your ear, then you hear it. 256 times every second. I'm going to show you a picture real quick. So this is kind of an image of literally what's happening. So I strike the tuning fork, and it makes the tuning fork go back and forth, and that squeezes the air. Do you see that? It squeezes the air, and it makes a what kind of wave? A longitudinal wave, right? So it's not that spring, but that air gets squeezed and stretched and squeezed and stretched. Do you remember what those things are called? Those squeezes and stretches. What was this part called? Yeah. This one's the compression. And then this one over here, the spread outy one is the rarefaction. Right? And so that's exactly what's happening. I'm going to show you one more. This is like a super quick little video, just again to kind of see what this looks like, because it's kind of nice to get the image in your brain. So this is literally what's happening. So these are like little air molecules. Okay. that are getting squeezed. So you got your little compression here, and then you got that space that they have the rarefaction, and then the compression. Does that make sense? So that's literally what's happening when I strike that tuning fork. It just bounces back and forth and back and forth.
So we hear
So
all
fast.
this stuff coming off of it.
So literally what's happening is that the air is getting squeezed and stretched and squeezed and stretched. So it's squeezed when it gets pushed together, right? And then it's like an absence of squeezing. So that's where that, like, it's kind of like a little vacuum that happens there. And that's moving air. So the air moves right here and squeezes. And then the air moves right here. And then it moves here and it gets closer and closer. And then your eardrum, which is literally just a little membrane, okay, gets pushed by that. And by getting pushed by that, then it transfers into your brain, into your auditory system. Auditory system to brain, I guess, is a more accurate way to say that. Can you ask a question? Are you sure?
Yeah. We get that all much better.
Yeah. Well, and how long does it take? So this thing is bouncing back and forth. Let's think about the numbers here. This thing is bouncing back and forth 256 times every second. How long does it take that little compression that happens here to get to your ear? How fast does the sound wave move? That would be another good thing for us to write down. Do you remember? In air.
331 plus 0.6.
Yeah, blah, blah. We don't have to memorize all this silliness. But yeah, you're right. It's so the speed of sound. So I'm not trying to say that you're being silly. I'm just like, you don't have to have it memorized. But just the idea, right? The speed of sound in air at room temperature is about 340 meters per second. Okay? You would absolutely not need to memorize that value, but it's nice to kind of have a sense of what that means. Yeah.
My brother has like a bronze bowl,
Okay?
and he'll like hit it on the side and then go around.
Yeah.
With a stick. What is happening there? Because like the sound gets louder.
We're going to talk about that at the end of the day today.
Really?
Yes, we are actually. So yeah, you need to keep me honest and make sure that at about 12:45 I'm moving that way. Does that sound good? Well, I think we'll be fine. But yes, we are going to get there today. That's where we're headed. So we know all this stuff. Are we feeling okay here? Prediction now. Now that you know what happens in air when I strike this tuning fork, how do you think that the speed of sound changes, if at all, when the sound wave hits something more dense, like a liquid, for example? My chemistry friends know the difference between solids and liquids and gases, right? Tell me about the density of a solid versus a liquid versus a gas. Which one's the most dense? What?
Solid.
A solid, right? Does that make sense? Solids have all those molecules that are just like stuck there and they're really close together, okay? A liquid is kind of in the middle, so that means the molecules are spread out a little bit, and in a gas, the molecules are just like all over the place, right? And I mean, there's pressures involved and whatever, but just kind of in general, we know that a solid is more dense than a liquid, which is more dense than a gas. Given that piece of chemistry, that's helpful to know. It's really physics, but we'll just call it chemistry because that's where you learn it. How do you think the speed of sound in water compares to the speed of sound in air? Think about what's literally happening to the molecules.
It's slower than faster.
Say that again. I just didn't hear what you said.
Slower in liquid and faster in the air.
Slower in liquid than in air. What do you guys think? Do you agree? Yeah? Yeah? Okay, let's just stand up. Make a line right here. Everybody, stand up.
When you go into
Wow, look at your handwriting today.
Is that what it is? The hard one?
Yes, sweetheart.
Is this supposed?
No, it should say speed. It's my job. What? I mean?
No, it's always me.
Oh, it's always you?
Yeah.
No, it's fine. You're good. All right. So based on the life experience that we just had, and hopefully now that you've had that experience, you'll remember this. Tell me about the speed of sound in a solid versus a liquid versus a gas. Where is it going to move fastest? It's going to move fastest through a solid. That's right. Okay. The speed of sound, speed of sound is going to be fastest here. And as we go this way, it's going to get slower. Okay. Oh, it's frozen, so you can't see all the beautiful stuff I just wrote. Thank you. I always forget. It's because I pause it, so like I don't have to record while you guys are standing up, since nobody will be able to see that anyway. So yeah, anyway, that's why I apologize. This is why it happens all the time. All right, so again, the solid is more dense than liquid, liquid is more dense than the gas, and the speed of sound is dependent on the density. Okay? So the speed of sound is going to be fastest through a solid and slower and slower and slower as you get to a gas. Okay? Way back in the day, and I would never, ever recommend that you do this. I want to make that very clear because it's actually quite dangerous. But sometimes you see movies where they do this, where like there'll be some kids that are walking along a train line, right? Like walking along, and then like, I don't even know why this would happen, but I feel like I've seen this in movies before where people like put their ear down to the rail line, you know what I'm talking about? Okay? And you'll be able to hear the sound of the train before you would be able to hear it in the air. Why?
Yes.
Yeah.
Stand By Me.
It's a great movie.
Where he gets leeches on him and stuff.
Yeah, yeah.
And he looks down and he's like, the train's
Classic,
coming.
exactly, classic. Yes, that's why, right? Moves faster through a solid. You with me there? What's up?
Possibly like blow out your eardrum if the train's like.
Well, the train could also hit you,
Oh, yeah.
right? Like that's the bigger
yeah.
issue. Right?
Just staying
Like,
until the
that is the problem that I want
No
to
one
avoid.
ever lived to know that.
Right. Oh, by the way, bad. Like trains are so dangerous because they're really, really big, right? Now, quick question for you. If a train, we're not going to put a person there because I can't even imagine that. A train hits a little box, like a little crate that's sitting in the middle of the train track. Does the train apply a force to the box?
Yes.
Does the box apply a force to the train?
Yes.
Which one applies a bigger force?
They're the same.
It's the same.
Yay! I'm so glad you said that. Made my heart happy. All right. You guys are great. Okay. Blah, 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 blah. All right. Now, we got a couple more quick things. And, okay. Yeah, we got to go. Woo! All right. Now, all of this stuff. Do you guys remember yesterday? You remember yesterday when you got really mad at me because I gave you that ranking task and you were led astray and you were upset and all of that sort of thing. Bamboozled, good word. And remember I said that it's really tricky because you had all the knowledge you needed, but you were trying to apply other knowledge that didn't actually work in that situation. You remember this? Yeah. Okay. So this right now is one of those times. So I'm giving you like the red flag warning, right? This is important. So
How did fifth period do with that question?
it was mixed. I probably presented it a little bit more clearly after my experience with you guys, but it was definitely kind of all over the board. Yeah. So this right here, I'm going to put in a big like highlighted box because that is true. That different pitches or different frequencies travel at the same speed in the same medium. But now, in the next part of our conversation, I'm going to put a big line. Okay? Now I want to talk about when a sound wave goes from one medium into another medium. Are you with me there? So we're changing kind of the structure of our conversation. So I just want to make that very clear. Okay? So here we go. When sound, that should be an N in there, hits a barrier. So that means a new medium, really, is what I'm talking about.
So, Ms. Guy,
Yeah,
is the air one medium and the wall another medium?
for sure it is.
Okay.
Yes.
Okay.
Or the air and the water,
Yeah.
right? Or the water and the wall. Or, I mean, like, it could be any two media, okay? But it's going from one thing to another. So when a sound wave When sound, I'm going to put wave there just to be very clear. That's what we're talking about, okay? Some of the wave will reflect. We saw that when we were out in the hallway last week with the big long slinky, right? I had a friend that was down at the other end of the hallway, and I can remember who it was. Matt, was it you?
Oh, yeah.
Were you holding the slinky? Oh, yes, I totally remember this. Yes, the finger abuse that was happening. Yes, yeah. And I sent a wave down, right? And the initial medium that it was in was the slinky, or that big long spring thing, okay? And then this was not a sound wave. This was just another mechanical wave, but any mechanical wave is going to do the same thing. It hit a barrier. The barrier was what? What was the barrier? What was the new medium that it hit?
His hand.
His hand, right? So we had one solid into another solid, but they're two different media, okay? Some of the wave did reflect. We saw that. We saw that part. So some of the wave reflects, okay? It bounces off, we'll say, into the original medium. I don't know, I can't spell right now. Original. There we go. Okay. If it's in the original medium, how does the speed compare? The incident wave and the reflected wave, how do they compare? It's the same medium. Same speed, right? Okay. There's no reason for it to be different. So if instead of it being one wave, it was a bunch of waves, right, or a periodic wave, they would have the same frequency. And if it has the same frequency and the same speed, what does that mean about its wavelength? Friendly reminder that V is equal to F times lambda. If this is 6 and this is 3, then what does this have to be? 2, right? So if the speed is the same and the frequency is the same, what does that mean about the wavelength?
They must be the same.
Same. True statement. Okay. What happened to the amplitude of that wave? Do you remember?
This way?
The one that when we were out in the hallway, when Matt was holding onto the other end of the spring, and I sent a wave down, and it went down. When it bounced back with the same speed, the same frequency, the same wavelength, that the amplitude was smaller. Yes. And we talked about it, but I want to remember why. So the amplitude decreased. Why did the amplitude decrease? It lost some energy.
Conservation of
Not
energy.
lost,
No, not lost.
but some of the energy went where?
Into his hand.
Into his hand. We're going to talk about that energy in a minute. So the amplitude decreased because it had less energy. Now, if we're talking about a sound wave instead of this springy wave, what does a decrease in amplitude mean? What does a decrease in amplitude mean? What is it?
Quieter?
It's going to be quieter. Yes. Or we could say a decrease in volume. Okay. This reflection of a sound wave has a name that you've heard undoubtedly many times. It's an echo. That's all that an echo is, you guys. It's just a sound wave reflecting off of a barrier. That's it. And if you've ever been in a room where you can hear your own voice echo, if you just say one thing, if you just go, oh, and then you hear the echo, every single time you hear it, tell me about its volume. Does it go down a little bit every time? Yeah. Because it's bouncing and bouncing and bouncing. Yeah. Is this making sense? Yeah, go ahead. Absolutely, you may. How are we doing?
Good, that makes sense.
Fantastic. So now we're going to throw a wrench into things because we're going to talk about the wave that doesn't reflect. Okay? Some of the wave reflects, but we're going to talk about the other part now. We're going to say also some of the wave enters the new medium. And the amount of wave that enters versus reflects depends on the types of materials. And there are lots of people that can tell you lots of equations about that. I don't really want you, like, you don't need to know that. All you need to know is that some of it's going to go, some of it's going to bounce, some of it's going to go in. That's what you need to know. Okay? Now, if it enters a new medium, my friends, that means that it might be changing from a solid to a liquid to a gas. It might be changing from one solid to another solid or something like that. What do we know about its speed? Is it going to be the same or is it going to be different? It will be different, and it does depend on the medium. It actually depends on that medium and the original medium, right? So it depends on both media together. Yeah. So we know that it's going to have a different speed now. Okay. We'll just make a little note here that the speed depends on the density of the new medium. That's consistent with what we said just a minute ago. I just want to make sure we have it written down there. Okay. The closer the molecules are, the higher the speed. We've said that already. Here's the thing that's important to know. Remember, we have this equation. V is equal to F times lambda. We're saying that the speed changes. Now, I'm going to ask that you take Matt's word for this. I don't have any reason to believe that he would lie to you. So we're gonna take him at his word. Okay? Matt, I have a couple questions for you. Okay? So when we were out there, you remember this day, right?
Yeah.
Your hand was starting to hurt because you're like, let's go, Carmen, let's do it. But you were toughing it out, and I appreciate that. Okay? I sent a wave down. Could you tell when the wave got to your hand? Like, could you feel it a little bit?
Yeah.
Okay, so he could feel it. So we know that. So we know that some of the wave entered the new medium. Now, if I just send one wave down, life is good. That's not very interesting in terms of our equation. I want to know about the frequency. Are you ready? If I sent down a wave every second, does that make sense? How often are you going to feel a wave going into your hand? What do you think? It's not a trick question. You'd feel it every second, wouldn't you? So that would be 1 cycle per second. Are you with me there? Then I'm sending it down. So the frequency of the wave, the original wave is 1 hertz. And the frequency of the wave inside Matt's hand, it's like going through his hand, with a frequency of 1 hertz. Okay? Let's say that I sent it down twice as fast and I send it down 2 times every second. What's the frequency if I send it down 2 times every second? 2 hertz. What's the frequency going to be inside your hand? 2 hertz. You with me? Let's say it was magical and I could send it down 30 times a second. He's like, yeah, right. That's not going to happen. It's not going to happen. Let's say I did. How often would you feel it in your hand? 30 times a second. Are you with me there? Okay. The speed changes. Will the frequency change? It will not. The frequency remains the same. This is weird, you guys. It's important, as you can tell, because I know that people miss this a lot. So I want you to know it, okay? When the wave changes from one medium to another, the speed does change because the density changes, right? But the frequency does not change. The frequency will remain exactly the same. Quick question for you. Does the wavelength change? Yeah? What evidence do you have that the wavelength changes? What'd you say? Does the frequency change? I'm calling you out because I want to make sure that you say it. Because and the reason is because a lot of people want to just say that the frequency is going to change, right? Because it just makes sense. The speed changes. And if you have this funny little equation over here, this velocity is equal to wavelength times frequency, and you know that the velocity changes, but the frequency remains the same, then that means that wavelength also must change. How are we doing? We're okay? Yeah? All right. Okay. Got two more pieces. So I kind of lied to you, Jordan, in that we're not really going to get to what I wanted to do today. But we will do it, I promise, when we get back from break. It'll give you a reason to come back because you need to know the answer to that question. I mean, not that you don't have other reasons to come back to, but I'm just saying. Just saying. Yeah, we'll talk about it, though. I promise. It'll be great. I was really excited to have it kind of be like our exit, but it'll just be our entrance back. All right. So we got one more kind of big topic that I want to make sure we cover. Can I move this up? Is that okay or not quite yet? Yeah. We did a problem, I don't know even when it was, maybe like on Monday or sometime. We were talking about pianos. Do you remember we talked about like the lowest note and the highest note and how the frequencies varied? Do you remember what kinds of numbers we were talking about and varying between? Does anybody have any recollection of that? The answer can be no, I don't remember at all, and that's okay too. I had to look it up. According to our textbook, and I don't honestly know if this is really true, like if this is a, grand piano or whatever, but I'm going to go with it because it's what I could find quickly. The piano's frequency range was 28 hertz to 4,200 hertz. That's a pretty big range. Are you with me there? That's a pretty big range. So 28 hertz, that's going to be the really high or really low? Really low. It's a low frequency, low pitch. That's that boom, boom, boom key that you play, right? 4,200, that's going to be really, really, that's the really, really high, like the super annoying one, right? Okay.
It doesn't carry.
It carries in a different way. It's like that, yeah, okay? The reason that I wanted to bring this up is because it's kind of interesting to compare this with what we're going to call the audible range. What does audible mean? Anybody know? What's that?
Yeah.
What you can hear. Yeah. Yeah. So the general human audible range is generally between. Well, actually, before I tell you this, I have to tell you just a really quick thing because I just think it's interesting. So, I was writing ACT test questions, right? And I may or may not have wanted to write a test question or a test unit that had to do something with frequency. I don't remember if it was that or if I was suggesting a problem for something else. Anyway, we're talking about frequencies. And I thought about saying something like, the human audible range is this to this. And it was interesting. I just have to show this because it's interesting. That I was told that we were not allowed to do that because not everybody has that audible range, and then people might feel excluded or discluded from the normal. It's really interesting because that was my reaction at first, but then you think about it, and you think about the thousands and thousands of people that take the ACT, right? And all of the different backgrounds they come from, right? And so if you have a kid who's taking the ACT and has a very, very limited hearing range, due to no fault of their own, do you know what I'm saying? It's just interesting. It's like, oh, yeah, that's true. So we had to word it in a different way, such that it would not make people feel discluded. I just thought it was interesting. So there you go.
The word typical, or would that make?
I don't think. I can't remember what, or if I just, if somebody just was like, no, we're not going to do that. I don't remember, but it was something like that. Yeah. Anyway, it's one of those little like life experience things that I thought was really kind of interesting and I had never thought about before. Anyway, I'm going to call it the typical human audible range for normal hearing. Okay. And then with the caveat that if you wear earbuds around all the time, you're messing with your audible range all the time. Okay. And if you are listening to earbuds such that somebody else can hear them when they're in your ears, you're killing your range of hearing. And that's going to like totally come back to bite you in the bum later. So just FYI. What's up?
So say you have like a CI, like cochlear implant, right?
Mm-hmm.
And would that, like listening to music all the time, that affects the range that the cochlear implant would be able to pick up, or like your brain would be able to hear?
So I don't know enough about those implants to know exactly how they work. Does that make sense? But I would not say that it's outside the realm of possibility. Do you know what I mean? I just don't know what the technology is and how it works. If it works with your ear or if it works with the signal that's actually transmitted to your brain. So I don't know. It's a good question though. I feel like that's something you probably look up, but I don't know. Yeah.
What are decibels?
So decibels they're essentially a way to quantify volume, right? But they're on a log scale, on a logarithmic scale. So I don't know if you guys have done log scales in math or in chem, but they get kind of ugly. So but the number of decibels can reflect how loud something is. And that's basically how much energy the wave carries. Yeah. And when we get to resonance, which is the thing we're going to do when we get back, then we'll talk about how that all relates to. It's all good stuff. All right. Let me tell you the audible range before the bell just decides to ring or something like that. I love your questions, by the way, so I'm not trying to dissuade them. I want to make sure I get this written down. So the audible human range goes from about 20 hertz to 20,000 hertz. Okay. It's a pretty big range. As you age, that range shrinks naturally, okay? Generally, it shrinks more from the top than from the bottom, but I think it kind of comes in from both sides. The evidence that I have that it goes from the top especially comes from life experience that I've had hanging out with my grandparents, okay? They had one of those really old TVs. So we're talking like the cathode ray tube TVs, like the big ones, right? That sometimes would have a really, really high-pitched, sweet, hum. Do you know what I'm talking about? This happens with a lot of older devices. Has this really, really high-pitched hum, so bad that I was sitting watching something with my grandparents. I was like, I cannot sit here. Can you not hear this? And I don't think I said it like that, but in fact, they could not hear it. There was this really high-pitched hum that just was constant all the time that TV was on. But they had no idea. Because it was way up, right? It was maybe, 19,000 or 20. It was very, very high. They had no idea it was there. And
Friends.
What's that?
I have a box TV also.
Uh-huh.
My mom went to go turn it on, and my brothers and I went over there.
Mhm.
We couldn't, and my mom's like, "What's wrong?"
Mm-hmm.
She couldn't hear that.
Same. Exactly.
Do dogs have
It's weird. We're going to write that down in just a second. Yes. Yeah. And they absolutely do. And there was something, this was probably 10 years ago. It's a long time ago now. But there was a kid, some, smart aleck kid, I think over in Britain, who made a ringtone for their phone that was high pitched. And so they could get, text message alerts or phone call alerts while they're sitting in class that they could hear, but all their older teachers couldn't hear. And it was this whole thing, right? This whole, I don't know, there was stories on the news and whatever about this. And this guy, that's kind of smart. That's kind of interesting. But then you have that young teacher, right? That teacher that's just out of college, and then they could totally hear it and totally busted the whole thing. Yeah.
At what age is your audible range the greatest?
I would say probably I don't know for sure. Because again, that's biophysics stuff that is super interesting. I just don't know. My guess would be that your audible range is the best when you're very young. What did you say? Yeah, and there is some development that happens after a baby is like just after they're born, but I would say like young child would probably have, but don't quote me on it. And if you find out something different, tell me because I'd love to know. Okay, got to stay focused here. All right, so that's like the normal in big air quotes audible range. Okay, we can go below and above that. If we go below that, so we're saying something like less than 20 hertz. So that's less than 20 cycles every second. Okay. That's called infrasonic. Okay. And there are some things that vibrate in that low range. The best example, oh my gosh, I have to look that up because it was really good. Anyway, earthquakes. So earthquake waves, those P waves, are sound waves. They're longitudinal waves that are moving through the earth, right? And they vibrate at lower than 20 hertz, 20 cycles per second. Above 20,000 hertz is called ultrasonic. Okay. So as Stella was just implying, dogs hear in the ultrasonic. Dogs can hear up to about 40,000 hertz. Bats can hear up to about 100,000 hertz. Dolphins can hear way up high too. I don't remember. I didn't write that one down. But yeah, it's also very, very high. Okay. Some of it is. Yeah. Some of it's over here. Yeah, as well. Yeah. The other thing that we use ultrasonic waves for are for ultrasounds. If you've ever heard of ultrasounds. And the reason that I bring this up is it's, one of those like things that I believe very strongly in. There are always people that believe that there are medical things that are very dangerous that really in fact are not. Like there are obviously some things in medicine that are dangerous and whatever, right? But ultrasound is something that is used very commonly for a lot of different things, but most kind of like well known is for having ultrasounds for a woman who's pregnant. I'm going to just pull this up here real quick. So if you've ever seen an ultrasound picture, this is just one that I found off of online. I should totally get one from my kids, but I don't ever think to do it until I'm sitting and talking to you guys. The way that an ultrasound picture works is that they take like a wand that basically sends out ultrasound, like ultrasonic waves. So high frequency waves that travel through tissue, okay? And then they bounce off of different types of tissue or different types of bone. And so just like the wave went through the slinky and then bounced off of Matt's hand, that's exactly what happens here, is that the wave went through the mother's tissue and then bounced off of the baby's skull, for example. Okay? And they can vary the frequency of the wave. And in doing so, you can actually get in and so you can like see the baby's heartbeat, right? Or you can see the baby's, like they can measure the baby's head, they can find the baby's feet or whatever. And this is true for a lot of other things besides babies growing in mother's uteruses, like broken bones and things like that also. But this is just one of those that's like very common and I just, But the point that I wanted to make is it is absolutely safe because it's just sound waves. Okay, so there's nothing like bad. It's just pushing. Just a little longitudinal wave. That's it. You had a question?
Oh, you said like stuff in science that's safe. People think it isn't safe. I thought you were going to say vaccines.
Well, that's a whole other issue, but that isn't physics related. I've got strong feelings about that as well, but we'll save that for another time. How about? Does that sound good? If you have not been keeping up on your homework, I would strongly encourage you to spend a little time over break doing that. And other than that, really enjoy it, you guys. This is going to be a beautiful break. It'll be great.
Oh, Miss Cat.
What's shaking?
Am I coming for a retake?
Yeah, when are you going to do that?